Okay, so I had accidentally ended the recording instead of just resuming the recording. So this will be part two to the exam two review. But I'll just continue from where I left off with the sound transmission through. So with the auditory system, the goal is to generate an action potential from a physical stimulus, which is sound vibrations in the air. So here we see that movement enters the ear, or the sound waves enter the ear here through the ear canal. This is your outer ear. Let me change colors so it's easier to see. And when they come into your ear, they will reach your middle ear. So this is your middle ear. And your middle ear is made up of these three tiny bones, and they have a really important job. Their job is to amplify the vibrations because these sound waves over here, they are traveling through air. And once they get to the cochlea, they will be moving through fluid. So these vibrations need to go from air into fluid, and they need to be amplified so that they have the same strength when they move through a slower medium like fluid. So that's the job of the middle ear, to amplify those vibrations into the cochlea. So this pink tongue looking thing is the cochlea. It is kind of rolled out here to just show kind of what's happening all together. And we see these squiggly arrows kind of moving in these directions. So fluid is moving through the cochlea here. So it's moving in this direction here. And on top of this blue middle part, we have these little hair cells sticking out. And when fluid passes by, it pushes these hair cells to the side. And when those hair cells get pushed to one side, they will depolarize. And that causes a receptor potential in the hair cells, and then the hair cells are connected to ganglion cells, where it will generate an action potential that your brain can understand. So at the level of the cochlea and these hair cells, that's where we transition or translate the physical stimulus to an electrical event that your brain can understand. So if we were to take kind of a box here on the cochlea and zoom into it, we would get this picture. And I pulled this picture just so you can see kind of better what's going on and to review the basic anatomy. So down here on the cochlea, we have the basilar membrane, and then on top of that, we have the hair cells, which are these purple cells, and then the neurons, which are the yellow cells. The neurons are the ganglion cells. So of the hair cells, we have the tectorial membrane. So fluid is going to move across the cochlea, and like I said, it's going to push those hair cells to one side, depolarizing them, generating action potentials. That's just another way to look at the ear. It's just a zoomed in picture of the ear. Okay, so for the rest of the review, I'll be transitioning into the cardiovascular stuff because your exam is heavily cardiovascular, since we spent a majority of the lectures talking about muscle physiology, autonomic physiology, and cardiovascular physiology. So I want to start by going over actually some skeletal muscle physiology. This picture I have here is also pulled from your textbook. Um, and it is a zoomed in picture of the neuromuscular junction. So the neuromuscular junction is looking at basically the synapse between the motor neuron and the skeletal muscle. It has a unique name, the neuromuscular junction, and the skeletal muscle is termed the motor end plate. So this part down here would be the motor end plate. Up here is the motor neuron. And this whole thing is called the neuromuscular junction. this motor neuron will go and release acetylcholine onto your skeletal muscle, and it will open these ligand-gated nicotinic receptors. So these ligand-gated nicotinic receptors are shown zoomed in here. And in class, we talked about them being uh, a ligand-gated sodium channel, which is true, but we see here that this picture also shows potassium leaving. So these nicotinic receptors move sodium in and potassium out. But the net result is sodium in, and that causes a depolarization. So the muscle cell will depolarize. So that is the net result, to cause a depolarization. But I just wanted to make you aware that the nicotinic receptor is technically just this kind of monovalent cation channel where it will let in sodium and let out potassium. So I just wanted to let you know that it's both sodium and potassium, but the net result is sodium in. All right, now moving on to cardiovascular stuff. This graph is pulled from my previous discussion on EKGs, where we talked about the action potentials for contractile cells. And we talked about the depolarization, plateau, and repolarization. So what I want to point out here is about this calcium plateau. So in class, we talked about after this cell depolarizes, it will repolarize just slightly, but then it will plateau here. And some questions that I got in discussion, and something I have maybe just mentioned in discussion, is it's kind of counterintuitive that if calcium is entering the cell here, if calcium is moving in, then why is this voltage not changing? The reason is that calcium is moving in, but at the same time, potassium is actually moving out. Potassium moves out here. Very slow, but it's moving out through potassium leak channels. So leak channels are just these channels on cells that are just perpetually open. They're just always open, and over time they just slowly let potassium leak out. So if potassium's moving out and calcium's moving in, the net result is a plateau. So they kind of cancel each other out. And then at this point, once that plateau ends, those calcium channels close, and then the voltage-gated potassium channels open. Voltage-gated potassium channels are not the same thing as the leak channels. And once these voltage-gated channels open, a lot of potassium moves out, and the cell will repolarize. So just that this plateau, it is due to calcium, but there's also potassium involved in it. And then we also talked about the importance of the plateau, so like why it was there. So just as a reminder, this plateau is there as a protective mechanism for your heart muscle. With this plateau, it gives your contractile action potential a really long refractory period. And that makes it to where your heart muscle cannot reach muscle tetanus, which is a muscle cramp. So it prevents your heart from cramping, so that you can stay alive and keep your blood moving throughout your cardiovascular system. Without this plateau, your heart muscle would be more like skeletal muscle, and it can reach muscle tetanus. So that's the importance of the calcium plateau. It prevents tetanus. So, I want to talk about the Wiggers diagram next, and I have these notes here, but I erased them and I will redraw them. So I've taken a little clip from the Wiggers diagram. I've taken the bottom of it, where it's general cardiac cycle. And what we're going to do is down here on the bottom in white, I have left pressure is at each stage of this, like atrial systole, isovolumic contraction, ventricular systole, all these things, all these sections, we're going to label what's happening to the left ventricular volume and the left ventricular pressure. And that's just going to be either up arrows, down arrows, or maybe no change. Those are our options. So let's look at the first one, atrial systole. So blood is going to come into the atria, and then it will go into the ventricles. So here, if this is atrial systole, that means that the atria are contracting. So let's think about what happens to the left ventricle during atrial contraction. Well, if the atria are contracting, they're going to be pushing blood into the ventricle. So we will get a small increase in ventricular volume. The reason why I wrote small next to it, we know that the ventricle receives about 80% of its blood via passive filling. So this atrial systole, it will push blood into it, but just kind of a smaller amount of blood. It won't go up by that much because the ventricle already has a majority of its blood before atrial systole. All right, but with pressure, if the atria are forcefully pushing that blood into the ventricle, then ventricular pressure will also increase. I'm going to erase this small to give myself more room. I'll put it right here. It's a small increase in volume. All right, and then let's look at the isovolumic contraction. So with the beginning of ventricular contraction, the ventricles start below the atrial pressure, but they need to eventually get above aortic pressure. So they need to have a huge jump in pressure in order to eject blood. So at the very beginning, if they are at a really low pressure, then the first thing they're going to do is exceed atrial pressure. When they do that, it closes the AV valve, and that creates heart sound 1. Until they reach aortic pressure. But that in-between part where they are building pressure, so this pressure is increasing, they have no change in volume because they have closed the AV valve, but they have not yet opened the semilunar valve. So if all of the valves are closed, that is an isovolumic phase. And if it's isovolumic, that means no change in volume. The next phase, ventricular systole. So systole is contraction. So during ventricular systole, we are going to see the ventricles pump out blood. So we should see a drop in their volume because blood into the aorta. During this time, they are still increasing pressure. So they're going to increase their pressure the whole time because the ventricle needs to be above aortic pressure. So we will see an increase in pressure because it will be forcefully pushing and squeezing the blood out of the ventricles. And we see volume decrease. All right, so the next phase is early ventricular diastole. So at the very, very beginning of ventricular diastole, the ventricles are at a really high pressure because they just finished contracting. So at the very beginning of diastole, the ventricles drop below aortic pressure. Aortic pressure, that closes the semilunar valves. So atrial pressure before they can open the AV valve. So during this phase, this is actually the isovolumic, I'm running out of room, isovolumic relaxation. So during that phase, we're going to see no change in volume because the ventricle is below aortic pressure but above atrial pressure. And it's going to be dropping in pressure because it is trying to dip all the way back down below atrial pressure so that it can get a new batch of blood. All right, diastole, this is once we have opened the AV valves again, meaning that the ventricle has dropped below atrial pressure. So below atrial pressure, passive filling starts. So this is passive filling here. So passive filling. And we get an increase in volume. And I'll put maybe 2 arrows here because this is the largest increase in volume that we see in the ventricles. And maybe on ventricular, no, I'll just leave it there. So during ventricular diastole, we do get kind of a small increase in ventricular pressure. We don't have a huge increase in pressure, but as it is receiving blood, it is slightly increasing in pressure. And then this next phase is atrial systole, and you might notice that this is what we started with. This is the cardiac cycle. It is a cycle, so this will just keep repeating. So after it has finished passive filling, the atrial will begin to contract. That will push the small amount of blood into the ventricle, and it will have a little jump up in pressure. I should lower that a little bit. It'll have a jump up in pressure. So this take these arrows and draw a graph with them, like a graphical representation of these arrows. What you would get is the Wiggers diagram. So we see that at every part of this, all we did is say, okay, pressure here is increasing, it's increasing here, pressure's decreasing here, increasing here. And then with volume, all we said is volume is increasing here, no change here, dropping here, no change here, increasing here, increasing here. So we just took the Wiggers diagram and turned it into arrows, something that's a little bit easier to look at. And I hope these arrows make sense that if the ventricle is contracting, it should be ejecting blood and building pressure. And if the ventricle is relaxing, it should be dropping in pressure and then eventually going to gain pressure, just slightly because of passive filling. So this is just kind of what you already know happens in the cardiac cycle. It's just the basic kind of movement of blood. All right, there's one more part to the Wiggers diagram though, and that's the EKG. So up here, let's write out our EKG. And the way we're going to do this is by remembering that the electrical events come before the mechanical events. So, atrial systole. Just before atrial systole, we should see the P wave. Before atrial systole begins. The purple is ventricular diastole. We should see QRS. Whoops, didn't mean to put that. We should see QRS. So this is QRS complex here. And, okay, I drew that bad. Let me redraw it. That's not much better. The QRS complex begins before ventricular systole begins. So the QRS, or the electrical event, has to begin before the mechanical event begins. And then the T wave would happen right here, and that would occur before ventricular diastole, before relaxation. So by knowing where we have the contractions and relaxations, we know how to line up the EKG, because we know that the P wave should start before atrial systole, and we know that the QRS should start before ventricular systole, and we know the T wave should start before ventricular diastole. So the electrical event precedes the mechanical event. But let's look at the Wiggers diagram. It's something you've probably noticed. Oh, don't know what happened there. Okay, so let's zoom in on the EKG part of this. And you see that the P wave half of it is in atrial systole, half of it is out of atrial systole. But still, start it did start before atrial systole, so it is still that the electrical comes first and mechanical is second. So it is still like that, but just be aware that technically the atrial systole happens towards the latter part or later part of the P wave. Same thing with the QRS. The ventricle systole begins kind of halfway through the QRS complex, but you still need it to be first. The T wave happens to line up more nicely with that rule. We see that the T wave happens entirely before ventricle relaxation begins. All right, so I hope that this drawing kind of made the Wiggers diagram easier to understand. And just as a reminder, the Wiggers diagram is just a graphical representation of the cardiac cycle, and it is just showing you what you already know happens in the cardiac cycle, like the movement of blood, what you think the pressures and volumes would be in terms of arrows, and the Wiggers diagram just plots that for you. Okay, so those were the cardiac slides I have for you, but there's one more kind of big thing I want to do to end this review. So I want to talk about this equation. Mean arterial pressure equals cardiac output times total peripheral resistance. And actually, I'm going to rewrite this and give myself more room. So if you're following along with notes, I suggest giving yourself lots of room for this next part. All right, so mean arterial pressure equals cardiac output times total peripheral resistance. So what we're going to do here is we are going to view of the cardiovascular system in terms of what factors affect cardiac output and total peripheral resistance, and how does that affect mean arterial pressure. So with your cardiovascular system, the whole goal or the big thing that you want to regulate is your mean arterial pressure, because your mean arterial pressure is the driving force of blood flow in the cardiovascular system. It's a way to quantify the pressure gradient. Without a pressure gradient, you do not have blood flow. So blood flow is referring to the amount of blood that's circulating in the cardiovascular system, and your mean arterial pressure is telling you that there is blood flow happening because the pressure gradient exists. So it's the perfusion of vital organs. It's to regulate your mean arterial pressure, which means we have lots of things that can affect it. All right, so we know that cardiac output is equal to two things: heart rate times stroke volume. So let's look at these. We know that you can, well, first So going back to heart rate, we know that heart rate can either be increased or decreased. The thing that modulates your heart rate is your autonomic nervous system. So your sympathetic nervous system and your parasympathetic nervous system. Those two nervous systems can increase or decrease your heart rate. So sympathetic would increase your heart rate, parasympathetic would decrease it. And when I'm saying that, I'm saying if they were to be activated. So if the system was activated, it would increase your heart rate. If parasympathetic was activated, it would decrease your heart rate. But we know that these two are antagonists of each other. We know that they go in opposite directions. And this kind of goes back to the car analogy I talked about in discussion. So the sympathetic nervous system, it can lower your heart rate if you downregulate the sympathetic nervous system. So that would be like in your car, you can decrease your speed by letting go of the gas pedal. And then with the parasympathetic nervous system, we said that it decreases your heart rate. That's like pressing the brake on your car, pressing the brake on your heart rate. But if you let go of the brake, your car will speed up just a little bit. So by letting go or down regulating the parasympathetic nervous system, you can also slightly increase your heart rate. But I've put these two signs here because this is when they are activated. This is when activated. All right. So with that out of the way, let's get into more detail. Like, how do they actually increase and decrease heart rate? Well, the sympathetic nervous system, we know that the target for heart rate is really the SA node. So the sympathetic nervous system is going to go to the SA node, and it is going to increase sodium and calcium influx. So it's going to increase the amount of sodium and calcium that enters the cell, and that is through the funny channels, so the IF channels. If it increases the permeability of sodium and calcium, that means you have a higher heart rate. You will have polarization. So the IF channels, funny channels, being responsible for that gradual depolarization. So increasing sodium and calcium through them means it speeds up that gradual depolarization. So you increase heart rate. So parasympathetic nervous system, it will decrease calcium influx, and it will increase potassium efflux. So that is decreasing calcium permeability and increasing potassium permeability. And then the net result is a decreased heart rate, like we said, because of the minus sign. So with the parasympathetic nervous system, it hyperpolarizes the autorhythmic cells further, and when the funny channels open, that gradual depolarization is even slower. So you have all right. So that's the factors that affect heart rate, and that's the kind of mechanism on how they're actually changed. Oh, I guess we should actually put some more detail on here. The thing that does this for the sympathetic nervous system is norepinephrine. And norepinephrine will go to an adrenergic receptor. The one on the SA node is the beta 1 receptor. So norepinephrine on beta 1 receptor increases the amount of sodium and calcium influx through funny channels. On the parasympathetic nervous system, it releases acetylcholine on muscarinic receptors. Acetylcholine on muscarinic receptors. So that will cause an increased potassium efflux, which slows the heart rate. All right. So stroke volume. And I think I need more room for this, so I'm going to extend that line over here for stroke volume. So there are three main factors that affect stroke volume. The first one is preload. The second one is contractility. And the third one is afterload. All right, so just like we did for the parasympathetic and sympathetic, let's put plus and minus on this. So preload has a plus, contractility has a plus, and afterload has a minus. So what that means is that if preload increases, that will increase stroke volume. That's what that means. Whoops. Same thing with contractility. If you increase contractility, you will increase stroke volume. But with afterload, it negatively affects stroke volume. So if you increase afterload, you actually decrease stroke volume, and we will get there. But preload, the thing that influences preload is venous return. So preload is synonymous with end diastolic volume, EDV. That's just the volume at the end of diastole. So return is the amount of blood that returns to your heart from the veins. All right, so if venous return is the amount of blood that returns to the heart from the veins, what that's saying is if more blood returns to the heart, then there's going to be more blood in the heart at the end of diastole, which means there's going to be more blood pumped out. So that's how venous return increases stroke volume. Now, the things that can increase venous return is the skeletal muscle pump and the respiratory pump. All right, and both of these affect venous return positively. Muscle pump. We usually think of the skeletal muscle pump as being in your calf muscles. So the problem with the venous or the veins is that they are a very low pressure system in our cardiovascular. So to go back to your heart from your veins, it has to go through a very low pressure system and gravity. So blood that's coming up from your legs has to fight gravity in a low pressure system. So one way to counteract backflow of blood in the veins is that veins have valves in them. Backflow. So the skeletal muscle pump, what it's doing, like in your calf muscle, is it is squeezing on your veins. And when it squeezes your veins, it shoots blood up towards your heart. The reason why it only shoots the blood up and not downward is because of those valves that are inside of the veins. So the valves prevent the blood from moving down. So when your skeletal muscle squeezes the veins, it shoots the blood up towards the heart. Now, the respiratory to understand, but for the respiratory, it's really the inhale or the inspiratory phase of respiration. So if you were to take a really, really deep inhale, what you're doing is you are contracting your diaphragm and it's lowering, and then your intercostal muscles are pulling your rib cage open. And when you do that, you expand the volume of your thoracic cage, which is just your chest area. So if you widen the space of your chest area, you increase volume and you decrease pressure in your thoracic cage. That increases the pressure gradient from your veins to your heart. And we know that an increased pressure gradient or pressure gradient in general, is the driving force of blood flow. So if you have an increased pressure gradient, then you increase blood flow. So this is the equation I'm talking about. Blood flow is equal to your pressure gradient over resistance. The respiratory pump increases the pressure gradient, so you increase blood flow back to your heart. That's what's happening. contractility. Things that affect contractility. I'm going to erase these preload arrows. Okay, so the thing that affects contractility, there's a few different things. One of them is your sympathetic nervous system. And the other is the Frank-Starling effect. Sympathetic nervous system. So the sympathetic nervous system, it will release norepinephrine on beta 1 receptor, but more specifically, because we already talked about the beta 1 receptor, this is going to be the beta 1 receptor that is found in ventricular muscle. So it's the beta 1 receptor that's found in ventricular muscle, or in the ventricular myocardium. It increases contractility because it increases the calcium inside of the ventricle muscle. And we know calcium's role in muscle contraction. So it will be released from the sarcoplasmic reticulum, where it will go and it will bind to the troponin-tropomyosin complex and remove it from actin. That reveals the binding sites for myosin. So if you increase the intracellular calcium, you reveal more actin to myosin, so you have more cross-bridge cycles occurring. So you have more overlap between thick and thin filaments, and you get a stronger muscle contraction. So norepinephrine onto beta 1 receptors in the ventricular muscle will cause more myosin to bind to actin because of the intracellular calcium. All right, so let's talk about the Frank-Starling effect. The Frank-Starling effect is kind of the force-tension relationship, and it has to do kind of with preload. So what the Frank-Starling effect is saying is that if the left ventricle, if more blood enters the left ventricle, then the ventricle will be physically stretched more. So the more it fills, the more it stretches. And the more it stretches, the harder it will recoil on itself, kind of like a rubber band. The further you stretch a rubber band, the harder it will recoil on itself. So what the Frank-Starling effect is saying is the higher the preload, the more the stretch of the ventricle, and that increases contractility. So the more volume that fills the ventricle, the harder it contracts. That's what the Frank-Starling effect is saying. All right. So then the Frank-Starling effect is kind of influenced by venous return and the things that influence that. Afterload is always the trickiest one. Is a resistance that the left ventricle needs to overcome in order to move blood. So the thing that alters or influences afterload is vasoconstriction / dilation. So vasoconstriction will increase afterload. Vasodilation will decrease afterload. So if you increase vasoconstriction, you increase afterload. Increasing afterload would decrease stroke volume. I'm going to change colors here to show the dilation portion. If you increase vasodilation, or if you vasodilate, you will decrease afterload, and that increases stroke volume. So afterload has the negative relationship to stroke volume. So what causes the vasoconstriction and vasodilation. That's really your sympathetic nervous system. So this would be sympathetic nervous system. But more specifically, it is norepinephrine on alpha 1, which is found in the smooth muscle of arteries and arterioles. So alpha 1 and arterioles will cause constriction, vasoconstriction. So the more constriction you have in your body, the higher the resistance is through those vessels. So we're using this equation. Resistance equals 1 over radius to the 4th. So vasoconstriction decreases radius, which increases resistance. So increasing resistance means afterload increases. The heart has to overcome a higher resistance to pump out blood. So the sympathetic nervous system vasoconstricts, and that increases afterload. And then if you attenuate the sympathetic activity, you will decrease resistance, which will decrease vasoconstriction and decrease afterload. That's a very similar concept to vasodilation, but like we talked about in discussion, the sympathetic nervous system can't really dilate. It's mainly nitric oxide that does that, but we didn't really talk about nitric oxide in this class. All right, so I'm going to keep that resistance equation up because for total peripheral resistance, the things that affect it are also vasoconstriction and vasodilation. I'm going to move the resistance equation up here. All right, so vasoconstriction, it has a positive influence on total peripheral resistance. Vasodilation has a negative influence on total peripheral resistance. So this is very, very similar to afterload in terms of how it affects the target or the parameter that we are trying to change. So vasoconstriction, like we just said, is through the sympathetic nervous system, norepinephrine onto alpha 1. Vasodilation is either the removal of sympathetic activity or nitric oxide. But it's the same thing with resistance. If you constrict, you decrease radius, which increases resistance. That increases total peripheral resistance. So increasing total peripheral resistance increases really the afterload on the heart. So by increasing total peripheral resistance, you will increase mean arterial pressure because the heart has to work harder against a higher resistance. So that's the idea with afterload and total peripheral resistance, is if afterload increases because of systemic vasoconstriction, then the heart has to work harder to pump out the same amount of blood that it normally would. And if it has to work harder to pump out the same amount of blood, then it needs to kind of contract faster and harder. So you need more forceful contractions and you need maybe more frequent contractions as well. Okay, but this is kind of a big cardiovascular review, things that affect stroke volume, different types of pumps, stuff with the autonomic nervous system, the adrenergic receptors, beta 1, alpha 1, that sort of thing. So this is a really good thing to redo on your own to see how does everything work together, what is affecting what, and we will ask you questions about kind of conceptually how do we regulate mean arterial pressure, and the answer most likely lies somewhere within this. Some other things that we didn't account for in this is blood volume. It's really just blood volume. Total blood volume does influence mean arterial pressure, but we see that within everything that we just wrote, we didn't write total blood volume anywhere in here. that doesn't mean that blood volume doesn't affect mean arterial pressure. It still does. So your cardiovascular system is a closed system. So if you have more blood in that closed system, then it will just be at a higher overall pressure than a system with less blood. Volume does still affect your mean arterial pressure. Like if you sat here and chugged half a liter or a liter of water, your blood pressure would go up because you are physically adding volume to your cardiovascular system. But since blood volume is not directly kind of in one of these factors that affect mean arterial pressure, that tells us that altering blood volume is not the quickest or fastest way to alter mean arterial pressure. This is kind of like number 8 on your homework. Blood volume is not the fastest way to alter your blood pressure. The fastest way to alter your blood pressure, if we were to look at the things that are directly related to mean arterial pressure, if you want to increase your blood pressure the fastest, you would vasoconstrict. So your sympathetic nervous system. Your sympathetic nervous system vasoconstricting influence on mean arterial pressure. Okay, so that's all the material I have prepared for this exam review. I'm sorry it was in 2 parts. I accidentally stopped recording after dark current. But try to go back through this stuff. Hopefully the Wiggers diagram makes more sense. And then hopefully this mean arterial pressure equation gave you a kind of overall understanding of everything that's happening together. So I will see y'all in office hours, or you can reach me over email or Zoom, stuff like that.